Let's take a look at our day 5B note, focusing on equations of lines, 2D scalar, and in 3 space. There is a watermark on this video. I'm trying a new piece of software to capture the stream from my iPad, and we'll just see how that works. Hopefully I don't write too much that appears under the watermark. If there are issues, you can let me know and we'll try to change it again next time. Hands-on activity, so I would like you to try this on your own, or I'm going to assume you've already tried this on your own. And we are looking at the scalar equation of a line in 2 space, so R2, two-dimensional plane, 3x plus 2y minus 1 equals 0. And we notice right away that this equation is in standard form, so it's not slope y intersect form, it is in standard form. Random question, we'll just take a quick notice. What is the relationship of the vector n equals 3 comma 2 to the direction vector? And we could fiddle around with this in Desmos. We can see the equation here. We can change our y and our x value. We can put our equation into slope y-intercept form, or we can also write it this way, and you can fiddle around with that and see what that means. What do we notice about our equation here? Let's fiddle with it a little bit. We can find the slope. So if I put this in slope y-intercept form, 2y equals negative 3x plus 1. Y equals negative 3 over 2x plus 1. And what does that tell us about our direction vector? Well, remember, direction vector, we just kind of get that from the values of the slope. So m is equal to my run, which is 2, and my rise, which is negative 3. And do I see those values anywhere else? Yes, I do. They're actually, hey, you know, kind of like right here. Like maybe that has something to do with these values here. So let's just keep that in mind. And let's graph these. And let's take a look at, first, our vector n is 3 comma 2. So let's graph that on a graph, starting at the origin, over 3 up 2. This is n. And let's also add m to our graph. So what do we know about m? Well, it starts at the origin and goes to 2 comma negative 3 right here. And I don't know about you, but those vectors look pretty orthogonal to me. Let's actually test that, and we can do that by using the dot product like we've done before. So we want to answer the question, just to prove, is vector m perpendicular to vector n? Is m perpendicular to n? How are we going to find that? We can use our friend the dot product. So let's find m dot n, testing if it equals to 0. So remember, first of all, we're going to multiply our x components. So x of m, or m1 is 2 times 3 minus. Actually, we can put our actual values in here first, just for each vector. So m was 2 comma negative 3 dot 3 comma 2. Let's multiply those x components, 2 times 3, plus our y components, negative 3 times 2. So that's going to give us 6 plus negative 6, or 6 times 6, or 0. Therefore, we know that n is perpendicular to m. Excellent. So, have we proved that for any linear equation, ax by plus c equals 0, that the vector n, where it's defined as ab, is perpendicular to the line? Because we just did here. You know, we looked, we had our 3 and our 2 value from here that appeared here. We had our direction vector, which we got from our slope over here. And we just proved it, right? Well, we proved it for one specific example. So in order to prove something, I need to prove the general case. I can use a single counterexample to disprove, but that's not good enough for a proof here. So not so fast. We're not quite there yet. We only proved it for one specific case. So what we need to do is, rather than showing it for one specific case, we need to show this generally. So in general terms. So we'll let n be our vector a comma b. So we're getting those values from the standard form of my linear equation. What about m? Well, we need to define that in general terms as well. So let's start with our general linear equation in standard form. So we got our friend ax plus by plus c equals 0. And how am I going to find my slope here? Well, let's rearrange this into slope y-intercept form. So I'm going to have by equals negative ax minus c. Divide everything by b to get y by itself. So negative a over bx. Oh, that looks like that might be useful. And right here, this is our slope. And we're going to use that to define our direction vector. So therefore, slope is equal to negative a over b. And that means our direction vector m is equal to b comma negative a, like we've discussed before. So we have defined m, b, and negative a. All right, now let's consider the dot product. So we're looking at our general case. N and m are our general vectors. Oh, I don't need a question mark because it's a statement. Now let's consider, not can you consider? Let's show our values. So my values for n are a comma b dot my vector m, b comma negative a. And let's find our dot product. Multiply the x components, so a times b plus my y components, b times negative a. Tidy that up a little bit. So ab plus negative ab, or minus ab, because multiplication is commutative. So this is b times negative a, or negative a times b, or negative ab, or negative ba. They're all the same thing, so it doesn't really matter. I'm just going to write them both as ab in order to be a little consistent, and then it's easier to identify right away that they represent the same variable, the same product. All right, well, we already know about this. AB minus AB is 0. Anything minus itself is 0. So let's make a conclusion. Therefore, since we know that n dot m is equal to 0, we know that n is perpendicular to m. And we can also say something about n right away. It has a name, because by definition, we just proved that this vector n, which is just our a and our b value, is always going to be perpendicular to our slope, or our direction vector for our equation of our line for our line. So this is called the normal vector. So we're kind of saying that if we know the equation of our linear line in standard form, we like automatically, or very, very easily, know a vector that's going to be normal or perpendicular to that line. And remember, just as a quick recap, perpendicular, normal, perpendicular, orthogonal, right at right angles. Those all mean the same thing, and I'll often use them interchangeably as we go throughout this course. All right, in our example here, let's read through. Given that r is equal to 7, 1 plus t, 4, 3, and notice that's the vector form of our equation, so we can label that right away. Just to help us remember, it's not like it's a required part of answering this question. Vector form of equation. Find the scalar equation of the line. So we're going to have our standard form, ax plus by plus c equals 0. Oops. And we only have an x and y value, so we're just in R2 or 2 space. Oopsie. So scalar, we're going to need our normal vector a comma b. All right, let's work through this. First of all, do we know a point that lies on our line? Yes, we do. It's right here in the vector form of the equation. So point 7, -1, and our direction vector 4, 3. I need to think about our dot product. How is that going to be useful here? Well, we're going to need m dot n that equals 0. So we know my direction vector. I need to find the normal vector because that's going to give me the a and b values I need to put into the standard form equation for my linear line, my line. All right, lots of pieces to put together here. So what do we know about m? Well, m is 4, 3. N is what we're going to find out. So those are my a and b values equal to 0. Remember when we find dot product, we multiply the x components. So 4 times a, so 4a, plus my y components, 3 times b, so 3b equals 0. And we can think about what values will allow this to be true. So we could kind of rearrange and think like, well, 4a can equal negative 3b. What values could allow this to be true? Let's try a equals 3 and b equals -4. And let's do a left side, right side check to see if this works. Left side, 4 times a is 3. Right side, -3 times b is -4. And we're going to get 4 times 3 is 12. -3 times -4 is 12. Left side equals right side. So these values work for our equation. They allow it to be true. And so therefore we can define our normal vector as being, well, it's our a comma b. And so it's going to be 3, -4. Now we are ready to calculate. So I'm going to switch my color here. Now we are ready to calculate. Remember, we're trying to find the equation of the line here. We know the a and b value, but we don't know the c value. So we're going to use substitution, rearrange, and solve for a missing value. So ax plus by plus c equals 0. I know my a value. I know my b value. I know a point on the line, so I know an x and y value. And I'm just going to need to solve for my c value. So let's plug those values in. A, we just found a value that worked, was 3. X, we're going to get from up here, is 7. Plus b, we just said was -4. We know a y value, -1. Plus c equals 0. Tidy up, rearrange, and solve. We're going to have 21 plus 4 plus c equals 0. Or if we rearrange and solve, c is equal to -25. Let's put it all together. And we will find that the equation of our line is going to be, therefore, the scalar equation is 3x, so we have our a value, plus by, well, I guess our b is negative, so I should just put a negative sign there, minus 4y, plus our c value, which is negative 25 minus 25, and standard form, the whole thing equal to 0. I'm just going to rewrite that. It looks a little messy. I'm not quite satisfied with that, although our values are fine. So the scalar equation is 3x minus 4y minus 25 equals to 0. So we started with our vector form, and we converted into our scalar form using what we already knew from the vector form. We knew a point, and we knew our m value, which we could find our slope from. Using that, we found our normal vector AB, and those values helped us complete our scalar equation of our line, or our standard form equation for a linear line. Well, I should say a line in 2 dimensions. All lines are linear. Let's take a look at our next example here. For the following, find a normal vector of the line and 2 points on the line. So let's see what we're working with. Well, once again, we have a standard form equation. We don't see a number in front of the y, so we know that's just an invisible 1. So that's my coefficient there, so my b value will be 1. We are in scalar form already, which is a nice bonus because it gives us the n value right away. All right, so n, our normal vector, is, as we said before, a comma b. I have those values here, so my a value is 2, and my b value is 1. Cool. Now we need 2 points that satisfy the equation. And in order to do that, let's just find our x and y intercept. Why do we need 2 points? Because the question said find 2 points on the line. So we need 2 points that satisfy the equation. So let's find our x-intercept. Or sorry, let's start with our y-intercept, which occurs when x equals 0. I know we know that. I still find it helpful to just add that right away, just so I know what numerical value is associated with y-intercept. So let's see what happens when x equals 0. So in my equation, I'm going to set x equal to 0. Plus y plus 6 equals 0. Rearrange and solve. 0 plus y plus 6 equals 0. Y equals negative 6. So I know a point on my graph, and that point is x is 0, y is negative 6. Let's find our x-intercept when y is equal to 0. So I'll write my equation out. 2x plus, instead of y, I'm going to put that 0, plus 6 equals 0. 2x plus 6 equals 0. 2x equals negative 6. X equals negative 6 over 2, or I'm going to simplify right away to save space. X is negative 3. And so this gives me the point, negative 3, comma 0. And honestly, this is all the information we needed to solve this question. We really can use any point we want. If we take a look at this in general terms, so we saw specifically that when x is 0, y is negative 6. When x is negative 3, y is 0. For any term x, what does y equal? Well, that's just slope y-intercept form. Let's find that real quick. 2x plus y plus 6 equals 0. Y equals negative 2x minus 6. And now we're just using a table of values to find x and y coordinates on our line, which, I mean, we all know how to do that. We've done that since grade 9. It's just we don't usually think to apply it in this context necessarily because we're all this discussion about vectors lately. But anyway, let's conclude our question here. So find a normal vector of the line and 2 points on the line. Therefore, the normal vector is equal to 2, 1, and 2 points. 0 comma negative 6 and negative 3 comma 0. And if we really wanted, we know we can plug in any real value for x. We know how to find y. We know the equation of our line in slope y-intercept form if we need it. And so we could make a table of values, just like you've done since grade 9 and earlier maybe. Moving right along, let's talk about lines in 3 space. So let's make it a little more three-dimensional